Hello and welcome. A very warm welcome indeed to everyone joining us for this live presentation and for anyone watching on catch up, accessing the recording. Um, we have apparently over 500 professionals registered for this session, coming from 70 different countries. So that is fantastic. My name is Toby Mitchnell. I'm a senior editor at PEI Group and the editor of New Private Markets, and I have the pleasure of moderating today's session. I'll just give you 30 seconds on New Private Markets. So we are an information service for those investing in sustainable private markets, covering infrastructure, real estate, private equity, and private debt. We cover trends in institutional asset allocation, and that's all underpinned by a database of investors, funds, and managers. And we're covering anything from ESG to impact investing on that spectrum. So clearly, climate plays a huge role in our coverage. So I'm delighted to have been asked to be the moderator of today's session, which will be run by Nicolas Schneider, PhD. Nicolas is a senior research engineer and macroeconomist at EDHEC Climate Institute, working with the climate scenarios research team. So his work is on the development of physical climate risk assessment methodologies implemented over sectors, time, and space to support the scientific needs of both the EDHEC Climate Institute and scientific climate ratings. I won't read Nicolas' full biography. All I can say is that Nicolas, you must be much older than you look because you've already had quite a distinguished career, it would seem. So the agenda for today, Nicolas will spend sort of 45 minutes introducing and talking through CLIRMAP. And at the end of this session, I will moderate a Q&A. So you can submit questions at any point during the session using the Q&A button at the bottom of the Zoom window. I'll then put them to Nicolas at the end. We'll try and get to them all, but if we run out of time or if a question requires a little deeper thought than the session allows for, we'll follow up in writing, or rather EDHEC will follow up in writing afterwards and circulate responses to all the registrants. So, without further ado, I should hand over to you, Nicolas, to introduce everyone to EDHEC-CLIRMAP.
Thank you very much, Toby. Thank you everyone for joining. So I am very delighted today to present to you EDHEC-CLIRMAP, which is a tool that maps out the geography of physical risks and its macroeconomic implication across different features. So in terms of the outline of the session, first I'm going to give you a sort of brief background around what is EDHEC-CLIRMAP. And then we're going to go through the methodology together. I will try to start off with the data processing, the elaboration of the estimation data sets, the macroeconomic framework, the climatic econometrics methodology, the delta method, and the projection inputs. And then all together, we're going to slide into the interpretation of the information given by EDHEC-CLIRMAP, particularly what does it say and what does it not say. So I'm going to also offer you a live trial. I think that's important so that we can together grasp a little bit more how to have our hands on this tool. And finally, for investors in search of regional answer, I will naturally answer questions as part of our Q&A, which will be moderated by Toby here present. So let's get started. So background, what is EDHEC-CLIRMAP? So just first, at the big start, I think the idea is that EDHEC-CLIRMAP reflects the commitment of our institution, EDHEC Business School, to advance rigorous and objective science-based climate research. We are slowly entering an era of growing uncertainty, particularly around climate. Although on the other side of the Atlantic Ocean, transition risks are being I would say reduced. The idea of physical climate risk has never left. And given the current policy of the Trump administration on the topic, it implies that physical risks will likely have a rising frequency and intensity in the most near future. Hence why it is important to understand the macroeconomic implication of these physical risks. So basically, EDHEC-CLIRMAP, as you can see in front of you, is an interactive tool. It is available on the EDHEC Climate Institute website, and it gives you basically a snapshot of the macroeconomic damage induced by physical climate risk across different warming scenario and global climate model. So you have a gradient of color in front of you that is indicative of the magnitude or the intensity of the expected changes, whether gains or losses. And the idea for you is to customize different parameters in order to observe different expected shocks. So in terms of the main competitive edge around EDHEC-CLIRMAP is first a highly resolved geographic visualizations of projected future climate change induced macroeconomic damages covering more than 3,660 subnational regions, therefore representing more than 95% of global economic production. EDHEC-CLIRMAP has a communication edge, which means that it translates its finding into intuitive, pedagogic, interactive, and transparent insights, which is an edge and a characteristic that is often missing in traditional research on the subject. And finally, EDHEC-CLIRMAP offers customization possibilities. You can customize local prediction across global climate model. I will describe further what it means. Warming trajectories under different climate scenario, and of course, future epoch or future periods of interest. So in terms of the documentation, so as part of our open access policy at EDHEC Climate Institute, all our tools are backed by objective peer-reviewed scientific research. EDHEC-CLIRMAP comes with scientific documentations on the topic. First, an exhaustive paper that presents the macroeconomic and econometric background. Second, a more synthetic note that gives you a sort of high-level view around the conceptual approach to computing macroeconomic damages. Third, a sort of how-to guide notes such that you can have an idea on how to use the tool. And finally, a more comprehensive academic aligned paper that is available on SSRN as well as on the EDHEC Climate Institute's website. So in terms of the methodology, how was EDHEC-CLIRMAP constructed? So if we take a step back together, we should just first ask ourselves, why are we doing this? We are all moving into a warming context. It is important to understand the macroeconomic implications of this warmer environment. Until 15 to 20 years ago, our approach to physical climate risk was mostly global, notably through the enumerative approach of NORDAOS, for instance. But yet we know, as you can see in front of you with this map, that climate change impacts space heterogeneously. So for instance, on the left-hand side, it's a spatial representation of surface air temperature anomaly distribution in 2024. And on the right-hand side is a snapshot of January 23rd, 2026. And what it tells you basically around climate change is that the world is big, weather exists, and what we understand now of the relationship between emission and temperature is that the spatial distribution of future physical risks will likely be highly heterogeneous, which implies that people, sectors, industries, countries will be heterogeneously impacted by physical climate risks. So one of the key points is to take into account this heterogeneity in order to give you insights around the future inequality story given by climate change on modern society. So if we move together into just the construction, basically EDHEC-CLIRMAP is made of 6 stages. You have first a macroeconomic framework, the elaboration of the historical data sets, then the running of climate econometric model, the construction of the projection data sets, the delta method to compute the damages, and then the most important part, which is the decomposition of resulting output across time, space, and many of other vectors of interest. So EDHEC-CLIRMAP seeks to answer 2 main questions. how local climate change-driven shifts in average temperature will damage regional economic production, and how do these region-level damage will scale up nationally and globally to shape our future understanding of the macroeconomic implication of physical risks. EDHEC-CLIRMAP finds its contribution by answering the two aforementioned questions. So first, the macroeconomic framework. So the idea is to start off something that has been well put in the literature in 2015, which is a modeling of how highly nonlinear short-range change in productivity can compound and sort of scale up, aggregate up into macro GDP responses over a longer term horizon. So to do that, you can basically represent yourself an economy which you can partition into multiple sectors, each sector is being contained by a group of industries that operate across different plants, across location being clusters of different productive plants. The idea is to set up a sort of production function, first at the macro level, where production factor, capital, and labor have each a specific productivity, and that productivity being a function of physical risk or, say, average temperature. The idea is that when you have micro level productivity shocks, they do affect profit and wages, and this has impact on the investment response and the capital accumulation, which normally aggregate up into GDP after factor reallocation. And so something to have in mind in that case is that when we talk about the global GDP response to physical climate risks, we really have to see that this is the aggregation of macro-level productivity shocks, which compound over time to produce change in the level of GDP. And so I'm not going to go further into this macroeconomic framework, but you can have access to the documentation where it is explained in details. So once we have this sort of framework to think about physical risk and plant production and macroeconomic production, we can move forward into the elaboration of the historical data sets. So something of interest in that case is to basically build a data set with historical data that links variation in economic production, particularly regional economic production, and historical fluctuation in a set of climate variables, and in our case, mostly temperature and precipitation. So to do so, basically, you have to start off with highly granular data. So in front of you is in number one is a very interesting map that I took time to build. So I think I will just go through it very quickly. The map in front of you basically tells you for each grid cell, so for each square of latitude and longitude, how large is the warming with respect to what the cell has normally experienced. To build this colorful map, I actually take the average of each grid cell and I fit a linear regression over a 16-year period. I get a beta, a linear trend in degrees Celsius per year, which I multiply by 16, which is my period, 2015, and then I compute the standard deviation, I normalize that to make it dimensionless, and I get a sort of trend effect, which basically tells you how temperature, basically how much warming has a cell experience with respect to its normal baseline. Something that is interesting in this case is to see the shift, which is a definition of climate change. And on our case, this is the data we use to then spatially intersect it with our region economic production. So something to have in mind in that case is that we have grid cells that are very small. And on the other hand, we have regions that are fairly big. And we need to match them together. And so something to do is that you can aggregate the information that all grid cells within the boundary of one region give you, and you can weight that with the population density, and then you end up with a sort of measure of the average historical climate information over a certain region, accounting for the distribution of population. Why are we doing that? Well, when we take the average, it's good to take into account some indicators. And on our case, something that is key is definitely the fact that people tend to concentrate where industries are. So instead of taking a straight average, something that is interesting in our case is that we weight using the intra-country population density distribution that is represented in 4. And that's what allows us to basically put more weight where people are located. All of this is trying to basically grasp and gather the most climate information possible and link it to variability in regions' economic production. On our case, so something that is particularly important also is that we are working with a large sample of data, which means that it's pretty long. So we work with the last 40 years of economic and climate information. And the idea is to then end up with a sort of panel data that links year-to-year variation in economic production per capita versus fluctuation in historical fluctuation in climate variables. Then once you have this data set ready, we haven't talked yet about anything related to future or to anything related to projections. The idea now is to quantify the global per capita gross regional product responses to historical fluctuation in a set of physical risk components. So this is a stage that is very important because we've been gathering historical data. And we want now to understand the relationship between our economic outputs and the fluctuation in these different climate variables. One way to do it is to run a panel fixed effect OLS model to control for a bunch of trend and spatially and temporary varying trending factors and estimate, quantify a response function, what we sometimes call a transfer function, which basically is supposed to represent the general relationship between our economic outputs and the fluctuation in historical climate variables. So in number 1, you can observe an inverted U-shaped relationship. This is aligned with the literature on the topic, which basically assumes that there is a turning point and each country is located on a different side of this curve based on their own climate average temperature baseline. And based on the country's location, its response to warming will be different. If you're on the left side of the curve, you're likely going to benefit from a rising temperature with respect to your baseline. That's the case for high latitude countries, for instance. If you're on the right-hand side of the curve, you're likely gonna be impacted negatively by marginal warming. And this is often, as we go on the right, you get closer to the tropics area. Something that is interesting also and that is very important to do is to run some robustness check. So something to have in mind in that case is that basically the impact of physical risk on the country is function of 2 things. First, the country's historical average temperature, this is country specific, and the country's future warming, which is also country specific. Something to have in mind as well in that case is that it is possible to run different regression and to empirically confirm that point estimates of the marginal effect of temperature on GDP per capita growth can be evaluated at different temperature baselines, and those will be similar to when baselines of GDP are included as control. Basically, what it tells you is that global nonlinearity is driven by differences in province average temperature and not GDP. So in our case, GDP is a determinant of countries' GDP deviation, income differences, but climate is not a destiny. The idea is to not say that countries are more impacted because they're poorer. The idea is to say that because of their specific climate characteristics, Countries have different average temperature baseline and different responses to future warming, and therefore this is what drives the future heterogeneity of climate change. Then the next step is the construction of the projection data sets. So the idea is to turn towards a very interesting tool, which is NASA's next GDDP CMAP6. So the idea is to rely on the latest climate simulation development driven by NASA and other mega providers, and access these large data sets that are available on cloud repositories. So these kind of data products are very heavy. They have specific file structures. Often these are raster layers. So it means like data sets with different georeference layers of data. And now people can access them using high performance computing system, which means supercomputers, and we can now touch this Alexandria library. So the example, for instance, of next GDP CMAP6, it's a group of researchers that have been able to use current climate change simulation and downscale them over time by days and over space, 25-degree resolution grid cells across different scenario and global climate model. So in our case, the global climate model are an important feature of EDHEC-CLIRMAP. Global climate model basically gives you a sort of understanding of the relationship between emission and temperature, which is not straightforward. And this ensemble of global climate model gives you a sort of confidence interval about what is the most likely response of temperature to doubling in CO2 emissions, for instance, and how should we expect other feedback channels, including clouds, to play out regionally and, more importantly, locationally. So the delta method in our case for projected damages, it's the fact that we will extract data, the future values of climate change simulation, say of future temperature values, for a specific period in time and say for a specific location and for a specific scenario and global climate model. And then we will take the inter-epoch difference, so meaning like between historical and future period. And that delta gives you basically the climate delta. What is the likely change in climate according to a certain scenario. And this is what you can force into your econometric model that you have calibrated prior. Hence why some of the quality of this projection depend inherently on the quality of the econometric calibration. Therefore, it is very important to carefully implement the stage 2 and 3 before going into the projection. Something to have in mind in our case is that once you have computed your projection, you can basically decompose the outputs. So you can decompose them across multiple vectors: country, region, years, climate scenario, global climate model ensemble. And the idea is to end up with a sort of end goal product, a vectorized product, a sort of big CSV file, where you will have for each location, for each region, a unique ensemble of estimated damages according to the scenario, SSP-RCP, the global climate model, the epoch, etc., etc. So on our case, you can see that we have 4 different models. So pool response, short-run effect, differentiated response, short-run effect, pool response, long-run effect, and differentiated response, long-run effect. What does it mean? Pool response is basically that we assume that there is one global representation of the historical relationship between economic output per capita and historical fluctuation in climate variables. Differentiated response is that we assume that these responses are specific to, say, income groups, and we therefore account for the fact that income groups may have different vectors of coefficient associated with the relationship mentioned above. Finally, something to have in mind is a short versus long-run effect. It is possible to account for the internal propagation of an impact, which means that a GDP of a country can be impacted in period T all the way to period T plus 10 or T plus 5. And this sort of propagation effect is actually plausible because we may assume that a physical risk impact or the warming of temperature may have sort of compounding multi-period effects that one should account for. So on our case, in number 3, it's a sort of map of if we were to plot, say that we take the median of some climate models and we account for a certain scenario. If we were to plot the distributions, if we were to represent ourselves and map out the magnitude of future damages, you can already observe a heterogeneity story. As you get closer to the equator, there is a rising magnitude and severity of expected damages. And as you move away and you move towards, for instance, high latitude location, we see diminishing impacts and also the start of net gains. And that is an important point to draw today. The conclusion of the macroeconomic literature on the implication of physical risks is that there will be net winners and losers in absolute terms. And that is something that is further told by the literature that works at the sectoral level. So on our case, then we plug our map into the EDHEC Climate Institute interactive website. And this is how you end up with a first representation of the economic implication of climate change. Something also to have in mind in our case is the fact that in front of you, you have administrative boundaries. This corresponds to administrative regions level 1, which are provinces. This is an international classification. And this is in between country level and county level. Country level, 185. Province level, 3,660. County level, 145,000. So you see the shift in granularity is also one of the current direction of the literature on the topic. In terms of extracting takeaway, so how to interpret information from EDHEC-CLIRMAP. I'm going to take a small break to drink. So if you go into on the website of the EDHEC Climate Institute, you will fall into this page and you can basically click on data visualization and choose EDHEC-CLIRMAP. So in front of you, I made screenshots of 3 main regions, the United States, Europe, and Asia. So basically when you log in, I mean, you don't even actually need to log in. When you go on the website, you can click on a specific region and it will give you the name of that region, the country it belongs to, the climate scenario, the global climate model, the future epoch, and for all of these different parameters, it will give you one unique number. So in terms of the climate scenario, you have the choice between SSP2 RCP 4.5, SSP5 RCP 8.5. These are moderate and vigorous warming scenario respectively. And we have also created a synthetic midpoint scenario that is our own production for this specific tool, which is an intermediate midpoint scenario between both moderate and vigorous warming. On that case, when it comes to Europe, so when it comes to Europe, we work with these provinces. So for the case of France, for instance, Région PACA, Région Rhône-Alpes. For the case of the United States, administrative regions level 1 correspond to states. And finally, you can move further down towards Asia and Australia and Russia and observe the different story that it reveals. To one of the points about also uncertainty, it's a very important point to have together. So uncertainty is a measure of how much we have yet to understand. And so to account for it, one of the solutions is to try to envelope it or contain it. For instance, on our global climate model, which again represent the relationship between atmospheric emissions and temperature, a relationship that is much more complex than we think. There has been a recent paper that is called the hot model problem that shows that some of them might be too hot. And therefore, we account for the fact that some of them might be too hot, and you can compute the median over a subset of 15 so-called likely global climate model. And that normally is thought deemed suitable to envelop this surrounding uncertainty around the climate model. Something else to have in mind also is the fact that our projections inherently depend on the downscaling method used to downscale CMAP6 output over time and space. So there is a sort of pattern that is latitude and longitude based. And finally, this is inherently driven by the quality of the nonlinear relationship that you have estimated prior using your climate econometric model. Now, in terms of extracting takeaways, how to interpret information around EDHEC-CLIRMAP. So EDHEC-CLIRMAP gives you a sort of snapshot of the regional distribution of relative gains and losses from physical risks. These gains and losses aggregate up to country, and they do shape the global picture of climate change. For a while in the media, notably, when we were talking about climate change and physical risk, you will often get a sort of globally average number. And something you must have in mind is that behind this global average, there is a deep, widely distributed heterogeneity story. And so sometimes what is hidden by this global average is this locally very diverse implication that are inherently function of the location of the country, its sectoral characteristic, or its economic characteristics. Now, how has the balance of forces played out geographically? EDHEC-CLIRMAP gives you an answer, but what it doesn't tell you is the sector-specific implication. If we think together, GDP being equal to the sum of the sector-specific value added, it is possible to compute sector-specific damages and aggregate them up using the share of each sector in the GDP, and to fall back into the number of the literature on the GDP damages from climate change. When you see curves around basically the GDP damage function with GDP, you have to think that behind each of these curves, there is a sort of umbrella of 20 to 25 different sector-specific curves that each of them increases the distribution much more than the global average does. So finally, could technical aspect of the production system offset the future losses from physical risk? That is a sector-specific deep dive. There is a very growing and booming literature on the topic of agriculture or energy, and that is where also the literature is currently going towards. I am going to leave back the mic to Toby to see if any of you has questions.
Thank you, Nicolas. I'll give you a little break and a little sip of water before talking. We have got quite a few just technical questions in terms of how the product works, which is understandable. So I wonder if we can whiz through some of those and then ask a little bit more about, again, interpreting results and putting that into a wider context. So some of these I think might be quite short answers. One question is, are the R scripts or data sets available to the public?
Yes. So the underlying data and one of the main goals of EDHEC-CLIRMAP is to only rely on free, open access, publicly available data.
Okay.
And something to have in mind also is that then we put that into our machine, we build output data, and that output data is available upon request to the EDHEC Climate Institute. We decided to not put it right away open access because we also wanted to have some feedback and interaction with people right away. But if you go into the documentation of EDHEC-CLIRMAP, you will see that all data are freely available and downloadable from your own computer.
Okay, and then a related one to tack onto that is can the data be downloaded via API or CSV export?
So this is a functionality we haven't put on the website yet, but this is currently under discussion. We do have the data on the background. This is what generates the map and allows us to basically update it with the different customization features. Yeah, reach out to us. Reach out to us. Reach out to Mode, and we can chat about it and potentially provide you data. Yeah.
Okay, okay. We've actually got a reams of questions, so I'm just going to try and. So here's a question that is: what do you think some of the main advantages of your approach are over modeling done by NGFS? Sorry,
NGFS.
NGFS. Yeah. And
Yeah, this is a very interesting point. So basically, for everyone in this call, so NGFS is a global provider. It's a very transparent provider of estimates of GDP damages across different scenario and integrated assessment model. NGFS is a gold standard. I think it's very important to say. NGFS has a physical risk module, particularly in its NIGEM module, that already incorporates an extremely relevant study on the topic made by Kotz and al. In 2024. Although there is ongoing debates with some specific critics that were addressed to that study, it is important to re-emphasize the methodological contribution that that study made, and that's why NGFS is that relevant. On our case, I think something to have in mind is NGFS works at the country level. We are able to work at the region level. NGFS gives you basically damages, for instance, on the NIGEM part that go all the way to 2050 for basically a sample of 49 to 52 countries. The idea of EDHEC-CLIRMAP is that it brings you all the way to 2100 and gives you a coverage that normally should gather and represent 95% of global economic production. It is possible to make EDHEC-CLIRMAP output compatible with NGFS output. EDHEC-CLIRMAP again is SSPRCP. NGFS has its own scenario, transition risk first, that they added a sort of temperature magic module onto it. But it's basically possible to make these two different toys interact pretty well. I think one of the advantages that we have is that for the calibration of our econometric model, we start off highly spatially disaggregated climate information. We particularly processed hourly data, and so we are dealing with an enormous matrix because 250,000 location times 24 hours times 365 days times 40 years, and then that times scenario global climate model. The resulting dimensional matrix is pretty big, and so one of the main challenge we have is dealing with dimensionality. Everyone wants to play with big data sets, but no one wants to deal with the obstacle it causes in terms of infrastructure. I think that over the last 10 years, the literature has seen a sort of booming technological advancement in supercomputer and high performance computing system. And now from where you are located with Wi-Fi and coffee, you are able to access via these supercomputers, these large databases. You're able to process them, to aggregate them, to average them, feed them into your model, run projections, and finally get a grasp around the heterogeneity of climate change impact.
interesting. And so we've got a few questions on various inputs, I'd say. One is, how do you account for the impact on the informal economy that's one of the main GDP contributors in the global south?
So this is an excellent point. One of the limits we have is in trying to understand the relationship between climate and economic output. we decide to rely on historical data. And we rely on historical data to try to understand this relationship. Some people do differently. We decide to do otherwise. However, one of the limits inherently is that we need to trust the quality, the inherent quality of the data we're gathering. For instance, it has been brought by the literature that the subnationally reported economic data on Uzbekistan, for instance, was potentially biased, and global results will be overly sensitive to this specific country and therefore should be dropped. On our case for the informal economy, we unfortunately cannot have a real grasp around what is not incorporated into the GDP as provided by the country's host. However, something we do account for is this sort of uncertainty, which uncertainty goes around climate uncertainty, model uncertainty, but also basically scenario uncertainty. And so when we mention the word uncertainty, basically what we try to do is to give boundaries to our results such that the most likely output will be sitting within our confidence interval.
Okay, and another quite specific input one here. You mentioned the importance of cloud dynamics in climate modeling. So this question reads, my understanding was that this parameter is very significant but cannot be reliably modeled because it requires spatial and temporal granularity beyond current capabilities. Could you elaborate?
Yes. So that's an excellent point. So we have a very intuitive but very biased approach to understanding climate change. First, the relationship between emission and temperature can be lagged. So there could be sort of lagged effect. It's not instantaneous. And there is a lot of interaction effects with multiple other physical risk components or climate components. Specific humidity, wind speed, wind direction, solar radiation, precipitation, vapor pressure, etc. People who are climate scientists have been working a lot in developing this global climate model to basically better represent over space what is the likely local simulation of climate change effect on a certain variable, for instance, temperature. It is still a work in progress. In the last generation, the CMAP6 generation of global climate model, some people pointed out that some of them are too hot, and the cloud feedback modeling that was incorporated was either biased or overestimated or underestimated. Us at EDHEC Climate Institute, we are consumers of this data. We do not develop our own climate data sets. We consume, like people are consumers of NGFS, we consume peer-reviewed, published, open access data by NASA, trusting that the confidence interval it gives us a good representation of what's going to happen into the future. Of course, these generations of climate models, and particularly CMAP6, they have a new generation that will come out, for instance, CMAP7, and in that case, we will revise our projection, incorporating the most recent climate change simulations.
Thank you. Thank you. I hope that answers that question. Here's a quicker one, which may be impossible to answer. Which global climate model would you recommend to select as a starting base when using the interactive map?
So I will advise you to start off with the first one, actually, because the first one belongs to, I mean, I think the first one probably that is given to you might be Access ESM15, and normally it's basically it gives you a good grasp around our uncertainty. It's sitting in the almost middle of the distribution. And what we are talking internally is to basically, instead of giving you the global climate model specific simulation, is to give you just a median of all. We wanted people to be able to play with these different features, but we understood quickly that maybe more information was not better. And so one of the ways to deal with it is just multimodal median. Again, the idea is to envelop the uncertainty. And therefore, you will observe that based on the global climate model, you get a different magnitude of your projection. This is because of the model-specific structural assumption. We have to take it as it is, which is exogenous.
Thank you. So we have a few questions just asking to really recap um, the climate data that goes into the model. So I might try and merge a couple of them together. So are 0.25 degree air temperature and rainfall the only drivers used to model productivity loss?
Yeah, so on our case, and we have a version, we have currently a version in progress that incorporates average temperature, temperature variability, precipitation extremes, number of wet days, drought, etc., etc. In the current case, we focus on climate change driven shifts in average temperature. Yet, this is the most intuitive and the most central component of physical climate risk. So 2024 and 2025 literature on the topic has shown that you may be able to incorporate a lot of different components of physical climate risks, but the most important, the most dominant, the most central determinant and driving force of physical climate risk remains average temperature. Why? Because of our good understanding of the relationship between average temperature and productivity. Productivity at the production level, productivity at the plant level, at the sector level, and also of the implication it has on our production factors and how do they scale up into the GDP damages.
Excellent, thank you. I should just mention to anyone who's joined late, I said this as I mentioned at the beginning, a recording of the whole session will be circulated. So if you missed on something relating to the methodology I explained earlier, you can catch up. Here's a question that sort of plays into some of the things I was hoping to ask myself, which is great. So great technical insight into the model, thank you. I'm trying to get a sense of how close we are to decision useful information on a corporate or municipal level. What's the feedback been so far?
So it is an excellent question. CLIRMAP gives you output that can feed policy or commercial products, whether equity ratings, sovereign ratings, top-down methodology for portfolio indices, etc., etc. CLIRMAP also will allow you to do a rating of regions, for instance. CLIRMAP, from the feedback we got, we have a significant number of outreach, notably from either consulting firm from all over the world, including developing area. And the people we had were interested in combining CLIRMAP potentially with a sort of probabilistic answer, meaning being able to put all scenario together and give you one answer instead of scenario-specific answer. And particularly for the region, something that came out a lot was about basically understanding the risk of the region, diving further down than the country level and giving you a sort of quick grasp or relative rating of the risk of a region with respect to others. So that is a first point with EDHEC-CLIRMAP.
Thank you. Another question just on the sort of availability of data. How do you guarantee the accuracy of each country's GDP statistics? This questioner says that they believe the open source data is inaccurate even for developed countries.
It is an excellent point as well. I like the question of today because you are raising very relevant known caveats. You have to use a GDP information given by countries like the inflation rate information or the interest rate information given by Federal Reserves. When the Federal Reserve or the European central banks gives you information about inflation rates, you stand as a consumer of this information. Whether that information is biased or not, overestimated or not, you unfortunately cannot do anything else than consume it like everyone else. So you are exposed exactly the same way. On our case with EDHEC-CLIRMAP, we rely on publicly provided GDP information or gross regional product information, whether from the World Bank or the IMF or any other institution. We use GDP deflator to try to harmonize the currency, work with chain link volume, etc., in real terms. But in the very end, what you are highlighted, and I think the question behind your feedback is the fact that to understand the physical risk implication and to adapt to it into a future, you need to know your exposure. To know your exposure, you need data. To use it to get the data, you need to basically access the climate and economic data and then run your model and run your projection. So we are inherently dependent on the quality of the available data. That's why the momentum that has started, the spatial momentum that has started over the last 10 years on the climate economics literature has been made possible because of highly spatially resolved climate change information. One, high performance computing system to deal with these big matrices. Two, and also some computing improvement to run this kind of large scale model and run these projections. Our understanding of the macroeconomic implication of climate change remains dependent on the data availability. There is some people, for instance, that have been working at offering more spatially disaggregated measures of economic production, and they use nighttime light data from the space to basically distribute country-level population over space within a country. That's an example of significant work that is being done in 2025 to get a deeper understanding of the intra-country heterogeneously distributed economic information. And that's something that is also of very high interest to us, is to understand that because climate change will impact space heterogeneously, some regions, particularly coastal area, and some population and some sectors will be differentially impacted. Because they have different responses, this will scale up into a different country and global measure of the true economic cost of climate change. Trying to capture this true economic cost of climate change cannot go without the best quality data we have. But right now, we work with what we have. And so my answer is to say that this might not be the best, but maybe the least bad answer, given the methodological and data constraints that are currently going on. We will be happy to improve it as data is available to us. And I think this is how science works. If we look at past studies with our today's glasses, we can have a grasp about the caveats and what improvement could have been done. But we also understand that maybe in 5 or 7 years, CLIRMAP could be outdated because newly available data allows us to do much better. And we will be present to collaborate to this end.
Good. We can squeeze in a couple more questions that we won't get through them all, that's for sure, and we won't get to any of mine slightly more layman questions. But as discussed, I believe Nicolas and team will endeavour to respond to each of these questions in writing, in follow up. So here's a question. My understanding is that you're correlating global warming / temperature with GDP, but how does that account for the impact of extreme weather events?
So CLIRMAP does not. So basically in the physical climate risks, there are two different subcomponents. There is acute physical climate risk and chronic physical climate risk. Chronic physical climate risk corresponds to the long stochastic warming process of climate change that follows an upward trend. This is a dominant force of climate change. Acute physical risk as these short-term, unanticipated extreme weather events that include flooding, wildfires, extreme heat wave, etc., etc. EDHEC-CLIRMAP relies on hourly historical climate information, but do not get a good grasp on acute physical climate risks. The reason is data. So our results will likely be underestimated with respect to acute physical climate risks. However, we focus rather on the long stochastic warming process of climate change, which is what is generating productivity losses that scale up into GDP losses. In understanding, wait.
Sorry, do you foresee a way of including those acute risks in future models, or is that just not quite compatible?
No, there will be methodological ways to approach it. The difference is, I think, the approach. Here we use panel fixed effect model to try to grasp the country-specific response to a long stochastic warming process. In acute risk, you will rather need to do some difference in differences methodological approach to understand the specific effect of an extreme event on your economic production or performance. Something that is possible to do, and the NGFS has done it, is to rely on an existing data set of extreme weather hazards and to basically incorporate the monetary value of extreme event impact as a percentage of GDP, for instance. And overlaying acute plus chronic should give you a better and more complete understanding. But this is hard. And as my mentor used to say, if it was easy, we will call it search. We call it research because this is hard. Playing with acute physical risk, it's a different area that requires a careful understanding of the methodology and of the availability of data. But there is a way to do it. So for instance, at the sector level, you might be able to use information, hourly information on extreme heat wave events and correlate that with energy demand, which is an adaptation strategy to outdoor temperature. And so there is a way to basically match high frequency output, say hourly or daily energy consumption to, for instance, the occurrence of high frequency extreme events that is very localized in time and space. There is work to do that, but the question in our case is because we are constrained by the temporal frequency of our GDP and GRP realization, we unfortunately cannot get a good grasp of the acute physical risk impacts on our GDP.
Thank you, Nicolas. Again, fascinating answer. We have loads more really juicy questions, but we have run out of time, unfortunately, which is gutting. But so in the remaining few seconds of the webinar, I'd just like to thank everyone who's tuned in and specifically for your questions as well as your attention, and thank you to Nicolas for your insights. As I said, recording of this whole session will be circulated to everyone who registered, and as well as possibly not immediately afterwards, but in follow-up answers to the subsequent questions as well that we didn't get to. And with that, yes, I would just like to say thank you to you all and goodbye, good afternoon, or good evening.
Thank you everyone for your attendance. Come to us, email us, contact us. We are always looking for partnership. We are an institute focusing on climate finance, and we will be glad to further discuss with anyone who is interested in reaching out to us. Thank you very much for your attention.